back to module 3 on finite difference method. We had already finished our description of basic methodology of finite differences, and in the last lecture we covered finite difference approximation of first order derivative. Today we would focus on the finite difference approximation of second order derivatives. So now let us have a recapitulation of what we did in the previous lecture. We discussed different approximation approaches for finite differences. Then we obtained finite difference approximations for first order derivative based on Taylor series expansion, and we also discussed a simplified general procedure on uniform grids based on Taylor series expansion, and then we discussed a method based on polynomial fitting. Now these methods were used to obtain finite difference approximation of first order derivatives. In today's lecture, which is third lecture in the series on finite differences, we will discuss finite difference approximation of second order derivatives. So let us have a look at the outline of today's lecture. We will have a brief introduction about the second order derivatives, why do we need to have an approximation for them, and then we will have a look at different approaches to obtain the approximation of second order derivatives. For instance, use of approximations which we have derived for first order derivatives. We can obtain ab initio approximations for second order derivatives based on Taylor series expansion. So we will say similar procedure which we have adopted in the case of first order derivatives, including a general procedure on uniform grids. We will take plenty of examples to explain the derivation process so that you can independently obtain similar derivatives of other orders as well. Then we will also have a look at the polynomial fitting approach in the context of second order derivatives. Now let us come back to this second order derivatives. Why do we need an approximation for second order derivatives? If you remember our derivations of the governing equations, whether we had dealt with the energy equation or a scalar transport equation, we had second order derivatives which appear in diffusive terms. Okay. So that is why if you want to solve our fluid flow problems using finite differences, we must obtain approximations for second order derivatives, and we can obtain finite difference approximation of these second order derivatives using approximations which we have derived earlier for first order derivatives. We can use Taylor series expansion or polynomial fitting. We can also use Pare approximants, and there are spline fittings and so on, but we are going to focus today on only these three, that is use of approximations of first order derivatives, Taylor series expansion based approach, and polynomial fitting approach. So now let us see how what allows us to use approximation of first order derivative. So for that let us have a brief look at the definition of second order derivative. How do we define it? Like del 2 f over del x square at I, this is second order derivative of function x with respect f with respect to x. This can be this is basically derivative with respect to x, that is del by del x of the first order derivative of f, that is del f by del x. Okay. So now we have already got the formula that how do we approximate this del by del x, this first order derivative, using finite differences. So our new function becomes, like right hand side can be thought of del by del x of gx, okay, where g is del f by del x, okay. And now we can use the first order derivative expressions which we derived in the previous lecture to obtain a finite difference approximation of this del g by del x. This one simple example here, like let us say we want to find out an finite difference approximation of del 2 f over del x square I. We can use simple forward difference scheme. So this will del f by del x at I plus 1. Now this you can think of del f by del x as gx. So g at I plus 1 minus g at I divided by xi plus 1 minus xi, and we have got plenty of choices we had forward difference scheme, we had backward difference scheme, we had central difference scheme. Any of those schemes can be used on this right hand side, and similarly for these two derivatives which appear in numerator, we can choose separate approximations. These could be backward differences or central difference approximations. So we would deal with, or we would derive these approximations of second order derivatives using formulae derived for FT approximation of first order derivative. Let us continue with the example which we cited in our slide. That is to say, we have used a forward difference approximation So let us have a look at our grid. This is a grid point xi, xi plus 1, xi minus 1. Now, in fact this is equal to del over del x of del f over del x at I. Now, for this term, now let us use our FDS. So, this becomes del f over del x at the forward point, that is x I plus 1, minus del f over del x at I divided by x I plus 1 minus x I. Now, we need to expand the first order derivatives which appear on the right hand side, that is del f by del x at I plus 1 and del f by del x at I. So, now let us use backward difference approximation for first order derivative on RHS. So, use backward difference scheme for first order derivatives. So, what do these become? Our del f over del x at I plus 1 this can be approximated in terms of the function value at I plus 1 minus function value at the grid point I divided by x I plus 1 minus x I. Let us write it in a more compact form using our delta x notation. So, this grid spacing, we have used the convention, we are going to denote by delta x I. and the spacing between the node x I minus 1 and x I, we will call this as delta x I minus 1. So, using this notation we can write our right hand side as f of I plus 1 minus f I divided by delta x I. Similarly, the second derivative, first order derivative which we had, so del f over del x at I. Once again let us use BDS approximation to make sure what we are saying. Let us just write the scheme name over the symbol. This is f I minus f of I minus 1 divided by delta x I minus 1. So, now we can substitute these two expressions in our previous expression and simplify it further. So, that will give us the finite difference approximation for our second order derivative. So, first term f of I plus 1 minus f I divided by delta x I minus second term, in place of del f over del x at I, we would write it f I minus f of I minus 1 divided by delta x I minus 1, and this whole thing divided by delta x I. Algebraic simplification is fairly straightforward. So, del 2 f over del x square at I, this is approximated by f of I plus 1 into delta x I minus 1 plus f of I minus 1 delta x I minus delta x I plus delta x I minus 1 into f of I, and our denominator becomes delta x I square delta x I minus 1. Okay. So, this is only one such approximation, because we have got a variety of choices which we can use first in obtaining this outer derivative, and then for approximating these inner first order derivatives. So, we can get a family of such a finite difference approximations for first order derivative. Now, I would like to leave it as an exercise for you, that verify or find out, this becomes an exercise, find out truncation error for the above approximation. This formula or this approximation can be simplified for uniform grids. So, let us see what would happen for uniform grid. So, let us write this special case for uniform grid. That is, our delta x I is equal to delta x I minus 1, and this we can write as simple symbol delta x. So, if you substitute it in the previous expression, we get the simplified form for this approximation, del 2 f over del x square at I, this is f of I plus 1 plus f of I minus 1 minus 2 f I divided by delta x square. Now once again I would leave it as an exercise, find out, or rather find out if TE for uniform grid approximation is O delta x square or O delta x. That is to say, just expand the terms on the right hand side in Taylor series expansion and see which are the terms which you have neglected in finding out this derivative. That will give you the expression for the truncation error, and so if it the results on uniform grid or any different from what you will get for non-uniform grid, that is, say if it is of the first order or it is of second order. Now this particular approximation which we have derived, that here we have used only forward and backward difference approximations, and both of these schemes we have seen earlier that they are first order accurate. Now can we expect to get somewhat better approximations if we use central difference scheme? So if you use the central difference scheme, we have already seen that we get much more accurate approximations using CDS. So now let us try and derive one approximation using central difference scheme. So use of CDS for approximation of first order derivatives now. In this case, once again let us have a look at our grid. This is the grid point xi, that is where we would like to have our approximation for the second order derivative. The grid point to the right of it xi plus 1, grid point to the left of it x of I minus 1. For CDS or central difference approximation, we need to choose the grid points which are just midpoint of these grid spacings. So one towards right, we let us call it as x I plus half, and the one at right we will give it as an index x I minus half. Okay. So now our del 2f over del x square at point I so is equal to del f over del x of del f over del x now let us use the CDS, that is, say we are going to use the function values at grid locations I plus half and I minus half, which are situated on both the sides of grid point xi. So if we invoke the CDS, we can write the approximation as del f over del x at I plus half minus del f over del x at I minus half divided by the spacing between these altered locations or the midpoint locations. So we can write it x I plus half minus x I minus half. So this is the expression which we have derived by applying central difference approximation to the outer derivative. Now, let us simplify the things a bit further. Let us have a look at the denominator on the right hand side, xi plus half minus xi minus half. This we can rewrite as xi plus half minus xi plus xi minus x of I minus half. As since xi plus half is midpoint of xi and xi plus 1, similarly xi minus half is the midpoint of this grid segment xi minus 1 to xi. The first one would be half of the grid spacing between xi and xi plus half. So, we can write this term as half of, the first term becomes half of delta xi. Similarly, our second term, that will also, this distance is basically half of the spacing between grid points xi minus 1 and xi. So, half of delta xi minus 1. Let us take this factor half outside. So, we can get a simplified form delta xi plus delta xi minus 1. Now, next we would like to find out the expressions for these first order derivatives. Once again let us use CDS. So, del f over del x at I plus half using central difference scheme. Let us focus on the grid point I plus half. The nodes to both of its sides are xi and xi plus 1. So, we have to use the function values at these two adjoining nodes whose midpoint is I plus half. So, that is we would use function value at I plus 1, that is fi plus 1 minus fi divided by spacing between these nodes, that is xi plus 1 minus xi, or using our delta x notation, this is f of I plus 1 minus f of I divided by delta xi. Similarly, for the next derivative which is involved on the right hand side, del f over del x, which is to be obtained at the midpoint of grid segment xi minus 1 to xi. So, once again this derivative can be approximated using central difference scheme using the function values at grid point xi and xi minus 1. So, that is this is equal to fi minus f of I minus 1 divided by xi minus x of I minus 1, that is f of I minus f of I minus 1 divided by delta x I minus 1. So, now we have got expanded forms for all the terms which we need in our previous CDS representation of outer derivative. So, let us substitute these expressions, and let us call the previous expression as 1, this is 2, 3 and 4. So, substitute equations 2 to 4 into equation 1, and the resulting expression would be del 2f over del x square at I, this is approximately equal to f of I plus 1 minus fi divided by delta xi minus fi minus f of I minus 1 divided by delta x I minus 1, and denominator we have got 1 by 2 of delta x plus delta x I minus 1. Simplify to obtain the final expression del to f over del x square at I. This whole thing is based on CDS or central difference approximation for the first order derivatives. So, f of I plus 1 delta x I minus 1 plus f of I minus 1 delta x I minus f I times delta x I plus delta x I minus 1 divided by 1 by 2 delta x plus delta x I minus 1 into delta x I minus 1. So, this is the final form of a CDS based or central difference approximation based approach for second order derivative. This expression, if you look, it is fair, numerator is fairly similar to the one which we have obtained using first order scheme, but there is small difference in denominator here. So, 1 by 2 delta x plus delta x I minus 1. What difference will it make to the accuracy of this scheme? That you can explore yourself by using Taylor series expansions. Let us have a look at simplified form for this expression for uniform grid. That is our delta x I is equal to delta x I minus 1, which we will call it a delta x. So, we get del to f over del x square at I f I plus 1 plus f of I minus 1 minus twice of f I divided by delta x square. So, this expression for uniform grid is identical to what we had obtained earlier. And just to give you a hint, the truncation error for this approximation is of order delta x square. That is this second, this central difference based approximation on uniform grid for second order derivative is second order accurate. Now, a simple exercise for you. Once again, obtain an expression for TE, that is truncation error for the approximation which we have derived on non-uniform grid for approximation five on non-uniform grid. As I mentioned earlier, that we have just discussed two possibilities. There are various other possibilities which you can use to obtain the expression for the second order derivative based on the expression for the first order derivative. So, remainders type of approximations you can explore yourself. Now, let us proceed further to the next approach, that is, let us use our Taylor series expansion ab initio So, once again a recap of what is our Taylor series expansion, which we have seen earlier, that for any continuously differentiable function f x, we had f x expanded around x is equal to x I. So, at any point x in the neighborhood of point x I, the function value is given as f x is equal to f of x I plus x minus x I del f over del x I plus x minus x I square by factorial 2 del 2 f over del x square I plus so on. So, can we use this expansion per se and perform certain algebraic manipulations to obtain an approximation for the second order derivative del 2 f over del x square at I. So, now let us try obtaining an expression for the second order derivative based on Taylor series expansion. So, let us get back to a writing board. So, use of Taylor series expansion. Let us first try to obtain an expression or an approximation of the second order derivative in terms of the nodal values at grid point I plus 1 and I minus 1, grid spacing as usual x I between these points and delta x I minus 1 would be the grid spacing between grid nodes x I and x I minus 1. So, for a recap, let us write our Taylor series expansion once again. So, f x is equal to f of x I plus x minus x I del f over del x at I plus x minus x I del 2 f over del x square at I square of this divided by 2 factorial plus so on. Now, let us write down the function values as we did earlier. We obtain the function values at grid node I plus 1 in terms of the Taylor series expansion at point x I. So, f I plus 1 this becomes f I plus x of I plus 1 minus x I del f over del x at I plus x of I plus 1 minus x I whole square divided by 2 factorial del 2 f over del x square at I and so on. Let us use our delta notation to write it in more compact form. So, f of I plus 1 is equal to f I plus delta x I del f over del x at I plus delta x square divided by 2 del 2 f over del x square at I plus delta x I cube divided by 6 del cube f over del x cube at I plus delta x to the power 4 divided by 24 del 4 f over del x 4 at point I plus and so on. Let us call these as our higher order terms. So, let us term this equation as 1. Similarly, function value at x I minus 1 is given by, let us write it straight away in terms of delta notation. So, this f of I minus 1 is equal to f I minus delta x I minus 1 del f over del x I plus delta x I minus 1 squared divided by 2 del 2 f over del x square at point I minus delta x I minus 1 cube divided by 6 del cube f over del x cube at point I plus delta x I minus 1 to the power 4 divided by 24 del 4 f over del x 4 at I plus remaining higher order terms. Let us call this equation or number it as 2. Now, our task is what we are looking for is to obtain an expression in terms of the function values at grid nodes and this grid spacing for second order derivative del 2 f by del x square. That we can obtain if we can eliminate the first order derivative from these two equations. So, if you look at the coefficient of the del f by del x I, in the first equation it is delta x and second one it is delta x I minus 1. So, all that we need to do is multiply the first equation by delta x I minus 1 and the second one by delta x I and add the two, thereby we would be able to eliminate the first order derivative. Rearrange the resulting equation and we should be able to obtain an expression for the second order derivative. So, let us do that. So, multiply equation 1 by delta x I minus 1 and equation 2 by delta x I and add. So, what do we get? On the left hand side we will get delta x I minus 1 f of I plus 1 plus delta x I times f of I minus 1. On the right hand side we will get f I times delta x I plus delta x I minus 1. The terms, these first order derivative terms, they get cancelled, they cancel out each other. So, the next contribution will come from the second order terms, that is 1 by 2 delta x I square delta x I minus 1 plus delta x I minus 1 squared into delta x I multiplied by del 2 f over del x square at I minus, rather from first equation we will get a positive term. So, this delta x I minus 1 delta x I cube divided by 6 minus delta x I times delta x I minus 1 cube divided by 6 and this whole thing multiplied by del cube f over del x cube at I plus the expressions coming from the fourth order derivative, their coefficients, they would be delta x I minus 1 into delta x I to the power 4 plus delta x I into delta x I minus 1 to the power 4 divided by 24 into del 4 f over del x 4 at I plus remaining higher order terms. Okay, now let us rearrange this equation and simplify, because our task is to obtain an expression for this del 2 f by del x square. Let us put this on left hand side, transfer everything else on the right hand side, and thereby obtain this expression for this del 2 f by del x square. So 1 by 2 delta x I into delta x I minus 1 delta x I plus delta x I minus 1 multiplied by del 2 f over del x square at I. So, this is a term which we keep or retain on one side, remaining go on the RHS. So, let us at one go have the functional terms, the terms involving the function values. So, we get delta x I minus 1 f of I plus 1 plus delta x I f of I minus 1 minus f I times delta x I plus delta x I minus 1. Now, the terms containing the higher order derivatives. So, we get delta x I delta x I minus 1 divided by 6 within brackets delta x I minus 1 square minus delta x I squared del cube f over del x cube at I plus the terms coming from the fourth order derivative. So, this we can again write as delta x I delta x I minus 1 divided by 24 into delta x I to the power 3 plus delta x I minus 1 to the power 3 del 4 f over del x 4 at I plus higher order terms. So, now we are ready to get the final form of the expression. So, this would be given by, therefore, what we get del 2 f over del x square I, this is equal to the function values, let us write them in numerator. So, delta x I minus 1 f of I plus 1 plus delta x I f of I minus 1 minus f I delta x I plus delta of x I minus 1. So, this completes our numerator part in terms of the function values divided by 1 by 2 delta x I delta x I minus 1 into delta x I plus delta x I minus 1. So, this is basically the approximation which we are looking for. Just put it in a big bracket. The remainder terms, they are in form of the multiple of higher order derivatives, And if you look at carefully, this is what we had obtained earlier by using central difference approximation of the first order derivatives previously. Now, let us also complete the higher order terms, or terms containing the higher order derivatives, which will form the part of a truncation error. So, it will be 1 by 6 of delta x I minus 1 minus delta x I times del cube f over del x cube plus higher order terms. So, we can clearly say that if we use this approximation, thus this approximation for the second order derivative del 2 f over del x square of I, this is delta x I minus 1 f of I plus 1 plus delta x I f of I minus 1 minus f I delta x I plus delta of x I minus 1 divided by 1 by 2 delta x I delta x I minus 1 into delta x I plus delta x I minus 1. So, this is the approximation which we have obtained for the second order derivative on a non-uniform grid using Taylor series expansion. How about its truncation error? Truncation error is the terms which we have neglected. So, first term which we will say that is the one which is multiplying our third order derivative, and formally this we will say this is of the order of the grid spacing delta x, but at the same time, so this T was, or this T is equal to 1 by 6 delta of x I minus 1 minus delta x I del cube f over del x cube I plus the higher order terms. Since here we have got a difference of the grid spacing, it is actually more than first order accurate. In fact, it is closer to the second order, or the T is more likely to be of the second order when the grid spacing is nearly uniform, because this difference would be fairly small. Then the next term is the one which will come into play, that will dominate over this term. The next term which multiplies this del 4 f by del x cube, that term in truncation error would dominate, and that is clearly of the order delta x to the power 4. You can just try and see if we assume our grid to be uniform. So, on uniform grid, that is delta x I is equal to delta x I minus 1, we get back our familiar expression which we have derived previously. So, this del 2 f over del x square at I, this is f of I plus 1 plus f I minus 1 minus twice of f I divided by delta x square. And you can easily verify from the fourth term, or the h term which I just left as such, this truncation error in this case of the order delta x square. Now, this simple 3-point scheme for the second order derivative, this has got a number of advantages, and this expression is very widely used, in CFD. If you want, you can use the Taylor series expansion to derive the approximations of much higher order, which will involve many more points, but as you can see from a simple 3-point case, we had to do considerable amount of algebra. So, if you use more number of points, the algebra would become more involved. However, in the case of uniform grid, we have got a simple general formula which can simplify our task. Like instead of guessing that which equation to multiply by what factor and then what sort of eliminations we need to perform, Chung suggested that look, on a uniform grid we can write the difference approximation for a derivative, and so we can write the difference approximation for second order derivative on a uniform grid as del 2 f over del x square at point I in terms of the function values at grid point I and neighboring loads by multiplying by some factors a f I plus b f I minus 1 plus c f I plus 1 plus d times f I minus 2 plus e times f of I plus 2 plus so on divided by delta x square. Now, these coefficients a, b, c, d, they can be determined from Taylor series expansions for the function values, this f I minus 1, f I plus 1, f I minus 2 and so on, and compare the terms on both the sides of this equation. We will get a set of equations which can be solved for to obtain the values of these numerical constants a, b, c, d. So, for instance, the 3-point central difference formula which we have derived previously, let us try this general scheme for that, and let us verify if we can get the same approximation. So, we will derive this 3-point formula using our general procedure based on Taylor series expansion in the next class. So, thank you. Let us wait for the next class when we would derive 3-point central difference, backward difference and a 5-point formula, and we will continue with polynomial fitting and few other derivations for second order derivatives.